So, we continue with a discussion on the architecture of ARM controllers, ARM architectures, ARM microcontrollers. So, this is the part 2 of our discussion, architecture of ARM microcontroller. Now, in this lecture, we shall be mainly talking about the pipeline features that are present in the ARM processor. Now, because the concept of pipelining may be new to some of you, so what I shall be doing? I shall be devoting more time in explaining the basic concept of pipeline, subsequent to which I shall very briefly tell how the pipeline in the ARM processors look like and what is expected to be gained out of it. Why do we use pipeline? What are the advantages that we have out of it? Okay? These are the concepts that will be covered. Now, let us start with the basic question, what is pipeline? What is pipelining? Basically, pipelining is a mechanism for overlapped execution. Overlapped execution means, well, we do not necessarily associate pipelining only for instruction execution, for other cases also, as we shall see. When you say that we are carrying out certain task, normally what we do? We finish a task, complete it and then start with the next task. Now, in pipelining concept, the thing is that even before we finish the first task, we start with the second task. Even before we finish the second task, we start the third task. So, different parts of the tasks can be carried out in parallel in an overlap fashion. This is the basic concept behind pipelining, right. Now, the basic idea behind this is that we partition the computation that is being carried out into k number of sub computation or stages. Like the total computation that was there, we try to divide them up into several pieces of sub computations. If there are k number of sub computations we can divide into, then it is possible to have very significant speed up, we shall see, maximum up to k. But the very interesting thing is that we are not increasing the cost by a factor of k. Well, we can have k number of processors, naturally we will be getting k times speed up. So, we are not doing that. By a very nominal increase in cost, we are achieving close to k speed up. So, the increase in cost is very nominal, right. This is the main feature of pipelining. Now, in the present context, we are talking about instruction execution, but pipelining can be used very efficient and effectively in other domains of computer processing also, during computation of arithmetic operations, during memory access of a vector of data. I want to load a vector of 64 words from memory one by one. There also the concept of pipeline can help a lot. But in the present context, since instruction execution is the only thing we are concerned about, so we shall not be going into too much detail about the other ones. Okay. Let us understand first the concept. So, we take a real life example which has nothing to do with computers. Let us assume that we want to wash some clothes. Think of a problem like this. Suppose I have built a machine M which can do three things one by one: wash, dry and iron. So, I give the machine a cloth, the cloth will wash it, dry it, iron it and output that cloth in the iron form. So, let me assume that the total time required for the doing the whole thing is t. So, pictorially I show it like this. So, I have my machine which does washing, drying and ironing, let us say R. The total time taken is t. So, if I have n number of clothes, then the total time required will be n multiplied by t, right. Now, let us assume that instead of a single very complex machine which can do everything, let me divide this machine into 3 smaller pieces, 3 simpler machines, one which can only wash, one which can only dry, and one which can only iron. Naturally, this will not be costing 3 times as compared to the original machine, this will be much cheaper. So, let us make another assumption, the total time earlier was t, let us say for each of these the time is t by 3, t by 3 and t by 3. So, that the total time still remains t. Now, it can be shown, we shall be seeing later in the next slide, that here for processing n number of clothes, the total time required will be only 2 plus n t by 3, 2 plus n multiplied by t by 3. See, earlier it was n into t. So, if n is very large, then this 2 can be neglected. So, you can approximate it to n t by 3. So, you see earlier the time was n t, now I have reduced the time to n t by 3. This 3 comes from the number of stages, I have divided up into 3 stages. So, I have got a 3 times speed up, but I have not paid 3 times more, right. I am using simpler machines. This is the concept of pipeline, but let us see how this expression is coming. Let us look at this diagram in an animated form. So, washing, drying and ironing. First cloth comes for washing. So, this will be taking t by 3 times. So, after it is finished with washing, this cloth 1 can go for drying, and when cloth 1 has come for drying, the machine 1 is free again, machine 1 can start with cloth 2, cloth 2 is being washed. Next step, cloth 1 is coming for ironing, cloth 2 is coming here, cloth 3 and so on, like this it will go on. So, you see after this machines are all filled up, means every t by 3 time here, here, here there will be one cloth coming out. Earlier one cloth was coming out every time t, but now in this case every time t by 3 a cloth is coming out. So, I am getting a 3 times speed up effectively, right. This is the essential idea behind pipelining. So, for cloth n, if you just calculate, so initial 2 time is taken for the pipe to fill up, and after that 1 t by 3 for every cloth, for n cloths n into t by 3, like this it comes. Now, extending the concept to processor pipeline, we want to increase the speed of a processor now. Suppose I have a CPU, I want to make it faster, I want to make it k times faster. So, I have 2 alternatives, I can buy k copies of the CPU and run k instructions in parallel. So, that is one way to have k times speed up, or I can divide the execution process into k stages of pipeline. So, instructions will be executing in a pipeline fashion, just like that washing, drying and ironing I mentioned. So, there also you can expect a k times speed up. So, alternative 1 is replicate the hardware k times, but if you do it, the cost will also go up k times, because you have to buy k copies of the CPU. Alternative 2 is split the computation into k stages. Here you are not multiplying the hardware by k, rather you are splitting the hardware into k pieces, very nominal increase in cost. Okay. But in order to do this, you need some buffering. Let us say actually if you think of the earlier example of clothing, when the first cloth your washing is finished, you want to give it for drying. So, you must keep it somewhere in between, so that you can accept the next cloth for washing. So, there must be a buffer or a tray between the machines. These are something called buffering requirements. So, for an instruction pipeline also we need some registers or latches in between the stages, which will be temporarily storing the data, the result of the previous stage, which will be used by the next stage for processing. Well, if you do not use these registers, then the previous stage can go on modifying this value. So, the next stage might carry out some wrong computation, wrong calculation, okay, because of that. Now, a k stage pipeline in general looks like this. There are k number of stages S1, S2 up to Sk with a latch or register in between preceding every stage. So, whenever a stage completes its calculation, it will store the data into this latch and it will take the data from the next computation into its input latch. Because if this latch was not there, then while the next calculation is going on, this input will go on changing, right. So, this calculation can become wrong. Okay. This is how it works. Now, let us carry out a quick calculation of the speed up and efficiency of a pipeline in the general sense. So, earlier we showed that calculation for that washing example. Let us say, let us consider tau is the clock period of the pipeline. That means, every tau time data moves from one stage to the other, a new data also comes tau, tau, tau like that. And T I is the time delay for the circuits that are there in stage S I. And I told you there are some latches in between, right. This latches delay will be DL. DL will be the delay of a latch, let us say. So, whenever you have the pipelines like this, these are the pipeline stages and there are some latches in between, these are the latches. So, what will be the maximum stage delay? See, this is T1, this is T2, this is T3. So, the slowest stage in the pipeline will determine that what is the maximum speed in which you can shift the data, because the slowest stage will become the bottleneck. So, maximum of Ti, let us call it tau m, the maximum delay, and to it you will have to also add the latch delay dl. So, tau m plus dl, that is what is your tau is, that will be your clock period, right. That is how you calculate the clock period. Now, the pipeline frequency will be 1 by that tau. Now, f will also be the maximum throughput of the pipeline if you are expecting one result to come out every clock. That is what I said earlier. Na? Okay. Now, with this assumption, let us try to make a quick calculation. The total time to process n sets of data. How do you calculate? Tau is my clock, with every tau a new data is coming. Now, k minus 1 clocks are required to fill up the pipeline. There are k stages. So, I need k minus 1 clocks to reach a stage where all the k stages are working on something. After that, every tau time there will be one new result being generated, tau, 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 right. So, k minus 1 into tau will be your initial time for the pipe to fill up, and then this n into tau for the outputs to be generated. There are n number of data to be calculated on data sets. So, n number of outputs. So, this whole thing into tau. This will be the total time to process n data sets. Now, if we have an equivalent non-pipelined processor, well, if you ignore the latch delays for the time being, they are small. then the total time can be estimated as capital N into k into tau. Let us say k into tau will be the total computation time, let us say for the non-pipeline processor. Capital N is the number of data sets, capital N multiplied by that, this will be the total time. So, in a pipeline, how much speed up we are getting? T1 divided by Tk, T1 was the original time and Tk is the time with pipeline. So, you have this. So, if this tau gets cancelled out, you get this expression. Now, as n becomes very large, if you divide by n, k by n, so it will become 1 as k n tends to infinity, this Sk approaches k. So, for a large number of data that you are processing in the pipeline, your speed up will be close to number of stages k. This is an important result. Okay. Now, there is another term we define called pipeline efficiency, that how much is the performance close to the ideal value. Well, this Sk we just calculated, this is the pipeline speed up, right. Pipeline speed up is Nk divided by this, and divide by k is the ideal speed up. I told that the maximum speed up can be k, as n tends to infinity, the speed up will tend to k. So, that is when the pipeline is operated at maximum efficiency. So, if I divide it by k, that k cancels out. So, I get a factor, this I can define as the actual pipeline efficiency. So, it will never be 100%, maybe it is working 90% efficiency or so on, I can say that. And another term which is of course not that important in the present context, pipeline throughput, number of operations completed per unit time, total number of operation is n and the time taken is Tk. If you divide it, you get an expression, this is pipeline throughput. So, this is how you can make some simple calculations for a pipeline. Okay. And this is a very typical plot I am showing, number of tasks n versus speed up for some various values of k. Let us say k equal to 4, you see as the number of tasks increases, the speed up increases, it levels to very close to 4. For k equal to 8, it levels to very close to 8. 12, it levels to close to 12. So, it will never reach 12, it tends to 12. Okay. It will never touch 12, but it will get closer and closer to 12 as the value of n increases. Here I have shown up to 256, right. So, here you will get some idea what is actually happening. Okay. Now, coming to ARM, I am not going into the details now, because this is not a course where I am teaching you computer architecture. Rather, I am trying to tell you that ARM uses instruction pipelining, and why pipelining is useful, that I try to explain. If I have a k stage pipeline, I can expect to have k times speed up. Okay. So, in your ARM 7 architecture, this is one particular processor TDMI pipeline. There are 3 stages: fetch, decode and execute, where each of these were executed in one clock cycle, that is the tau we are talking about. So, if everything else is fine, we are expected to get about 3 times speed up in terms of instruction execution. Similarly, ARM 9 has a 5 stage pipeline: fetch, decode, execute, memory, write. So, you can see something smaller things. So, within the decode, the register values are also read, whatever registers are required. During execute, the shifting, the barrel shifter is also working, ALU operations are also carried out, memory access are carried out here. During write, the results are written back into the register bank. So, it is done here. So, these captions actually indicate that. and for ARM7 everything was done during execute, register read, shift, ALU, register write, everything was done in execute. But in ARM9 you are making it more elaborate and more flexible. So, here this speed up can be maximum 5. So, you can improve on that. And in ARM7, just an example, just the way I said that wash, dry and iron, here fetch, decode, execute. So, first instruction is doing fetch, decode, execute, second instruction can start fetch here while the first one is being decoded, third instruction can start fetch while the first one is executing, second one is decoding. So, starting from the third clock you will be finishing one instruction every clock cycle, right. This is the main means advantage or purpose of a pipeline. And just one thing I want to mention here, this speed up of k that I am talking about, that is an ideal speed up. That is the speed up you can get when the pipeline is operating in its full speed. But sometimes you may see that due to some reason you cannot operate the pipeline at full speed. So, in those cases the speed up obviously will become less, much less than k. So, I am giving one example. Suppose there are some instructions which are executed in ARM, let us say these are all add instructions and there is one complex multi-register store instruction. Let us say I talked about multi-register store, load and store. So, multiple registers can be stored and loaded together. So, it will need multiple clock cycles. So, the idea is that normally everything finishes in one clock, one clock, one clock, one clock, this also proceeds. But for STR instruction what might happen, that this pink colored box, this although I am showing it like this, but this can actually require multiple cycles. So, what does that mean? Multiple cycle means here you cannot decode this next instructions unless you see unless this execute is over you cannot decode it. So, there will be some delay here because it is requiring multiple cycles. Such delays we refer to as stalls, we call them as stall cycles. Stall cycle means wasted, some cycles are wasted. You see here first instruction gets finished here at this point, second instruction gets finished here, but third instruction here, fourth instruction here, but because of this delay this instruction was supposed to finish here, but it got delayed. Not only this, all subsequent instructions got delayed and there can be many such instructions like this in between. So, for every such instruction there will be some stall cycle inserted, and once a stall is there, this stall will be carried by all subsequent instructions until that instruction exits the pipe, right. So, such cases can slow down the maximum operational speed of a pipeline. Okay? And just remember this. Just a bird's eye view of the ARM7, ARM9 and ARM10 pipelines. ARM3 I mentioned fetch, decode, execute. ARM5 also I mentioned fetch, decode, execute, memory write. In ARM10 there is just this additional stage of issue which has been inserted between fetch and decode. This issue is a feature which is an advanced architectural feature where you check whether to issue an instruction or not depending on various things. There is something called pipeline hazards, there can be data dependency, whether you can feed the next instruction or not. There are a lot of architectural issues which prevent the pipeline from operating at its maximum speed. Stall instructions can occur due to one example I gave because of a complex instructions, but there can be other reasons. There are situations called hazards, data hazards, there can be structural hazards, there can be control hazards. Because of various sequence of operations that are being carried out and some instructions like jumps and branches, you may have to insert stall cycles. So, all of these prevent the pipeline from operating at the maximum clock frequency. Just another thing, let me tell you, in this ARM 7 kind of architecture, a 3-stage pipeline, let us say when an instruction reaches the execute phase. Now, one thing you remember, I told you all instructions are 32-bit instructions. This we shall see later also in some detail. 32-bit instruction means 4 bytes, and your memory that you have, this memory is byte addressable. So, if the first instruction is stored in memory location 100, the next instruction will be stored in memory location 104, next location will be stored in location 108, because each instruction will be requiring 4 bytes or 4 memory locations, right. So, the point is that when some instruction is executed, the program counter will always be 8 bytes ahead. So, you add 8 because you will be fetching this. So, each instruction will be 4 plus 4. So, each instruction will be adding 4 to the memory address, and this program counter we shall see PC is a special register which always stores the address of the next instruction to be fetched, right. So, when you are fetching this instruction, this will be the program counter of the current instruction plus 8, because current instruction is here. If you add 4 to it, you will be getting the next instruction. If you add 8 to it, you will be getting the next to next instruction. Now, here you are always fetching the next to next instruction, right, because there are 3 stages. That is why the program counter is always 8 bytes ahead, you say like that. Okay. Because when you are executing, I have already incremented this PC 2 times, it is always 8 bytes ahead. So, that when you are fetching, you should accordingly adjust and fetch accordingly, right, that calculation is to be done. Okay. So, with this we come to the end of this lecture. Now, in the next lecture we shall be looking at some of the unique features of ARM with respect to the register organization, the various execution modes and so on. This we shall be discussing in the next lecture. Thank you.